All right, let's do the waves homework. Here we go. Number 1 says, 2 students stand 5 meters apart and stretch a tightly coiled spring between them. One of them generates a single wave pulse, which moves along the spring and takes 0.8 seconds to get to the other student. So we're looking at a situation like this where you have a student. They're holding like a slinky or something like that. And they send a wave pulse. And this is heading toward the other student who's going to catch it. Alright, so these 2 students are 5 meters apart. And it takes 0.8 seconds for the wave pulse to get down there. So number 1 says, how long will it take the pulse to get back to the generator? Well, it's another 0.8 seconds, because it takes 0.8 to get there and 0.8 to get back. One of the things that we talked about was the fact that the speed of a wave or a wave pulse is constant in the spring. 2 says, well, what's the speed? No problem. Thing we know about speed, we usually use a v, like velocity, but we don't care about direction. It's equal to the distance divided by the time. So the speed is equal to 5 meters divided by 0.8 seconds. So that tells me that the speed is equal to, what is that, like 6.25 or something? Let me calculate it. .25. That means that this wave can move 6.25 meters every 1 second that it's in the spring. 3 says, in a second experiment, the generator now sends a pulse that's twice as big as the original. So what if it were twice as tall? Like, whoa. Twice as tall. Will the pulse take more or less time to reach the other end of the spring? And the answer to that is, trick question, same time. One of the labs you did, you checked the amplitude against the wave speed. And what we know is the amplitude does not affect wave speed. Okay. 4 says, the students now move twice as far apart, stretching the spring and making it much tighter as they move. How will the speed of the wave compare to the original? Well, one of the things that we know from our lab experience is it will be faster. Tighter spring creates faster waves. It's the thing that the wave is in that matters. So if you change the thing that it's in by making it a more or less tightly coiled spring, it'll make it move faster or slower. What determines the speed? For this one in particular, what determines the speed? The tightness of the spring determines the speed of the wave. Tighter means faster. The students now create a wave by shaking it 10 shakes in 5 seconds. Find the wavelength of the wave. Ooh, this is a great one. So in this one, we're going to use our law that we developed in the lab. The law says that the speed of the wave is equal to the product of the frequency and the wavelength. Remember, this here is the Greek letter lambda. That's the wavelength. So that's actually what we have to solve for. In order to know the wavelength, is going to be speed divided by the frequency. But what's the frequency in this case? The frequency, well, it says you do 10 shakes in 5 seconds. So 10, each shake is a wave, so 10 waves every 5 seconds, the frequency is equal to 2 waves per second. And so if I put that in here, I know that my speed was 6.25, and I'm going to divide by 2, and it turns out the wavelength of my wave is 3.125 meters. There you go. There's the first set. Feel good about that. All right, let's look at the second set. Let me get my eraser. Reset. Oof. Oh, killed it. All right, so here's 7. So 7 looks like this. That's good enough for now. So this is A, this is C, this is F, this is D here. This is E. This line here is G. So I got them all. A, B, C, D, E, F, G. Okay. So fill in the blanks. A is a crest. B is a wavelength. C is the amplitude. D is a trough. E is also an amplitude. F is also a wavelength. And G is the equilibrium. It's the middle of the wave. So this is 7. 8's a little fill in the blank. So what do waves do? Waves carry we'll do it in green. Waves carry energy from place to place. This is 8. The highest points are the crests, and the low points are the troughs. The amplitude is the height of the wave. The distance from crest to crest is the wavelength. And the equilibrium is the center of the wave. There we go. Ooh, I like this next one. It's going to take some drawing, however. Okay, so 9 looks like this. Okay. All right. 9 says, underneath each, write the number of waves in a series. All right, let's do it. Let me show you what I notice. This is one full wave right here, because you have from the middle, then you go down, back to the middle, up, and back to the middle. So we have one full wave. It includes a crest and a trough. And you hit the equilibrium, basically the beginning, the middle, and the end. So this is one wave. All right, you can basically trace them out. So let's start here. So that's 1 and then a half. So that's 1 1/2. This one is 1, 2 1/2. This one's sneaky because it's actually only a half. The other half would be here, so this is just a half. So this is 1 1/2 waves. That's just 1. This is 1, 2 1/2, and that's just a half. Which wave has the biggest wavelength? And the answer is D has the biggest wavelength. So if you just look at the wavelengths here, here's the wavelength for this one. Here's the wavelength for this one. This one's bigger than this one. This one's got a pretty small wavelength, but look at this is a half wave, so the wavelength for this one would be huge. So D has the biggest wavelength. Which one has the biggest amplitude? You would actually have to measure. I tried to draw it this way, but the amplitude would be this height right here. So, sorry, let me get a better color. This would be the amplitude right here. So if you looked at yours and you tried to match them up, I think the biggest amplitude goes with A. That's the height of the wave. And then assuming each was made in the same time, which one has the biggest frequency? Well, the frequency is the number of waves per second. And if this was made in the right amount of time, same amount of time, this one has the most waves, and so C has the biggest frequency. Also, smallest wavelength, which gives you a sense that it has the largest frequency. Okay? Was it good? All right, let's do 13, 14, and 15. All right, so 13 says, a wave on Lake St. Clair passes by 2 docks that are 40 meters apart. There is a crest at each dock and another 3 crests between the docks. What is the wavelength of the waves? All right, so let's draw that. So we're going to look like down on it, okay? We're going to look down on it. So here's a dock. And then over here, 40 meters away, there's another dock. So if there's a crest at each dock and then 3 in between, I'm going to go crest, 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 crest. So I'm going to say there's a crest here, and then 1, 2, 3, and then 1 there. Okay. So this distance here, 40 meters. All right, that looks great. So it says, what's the wavelength of the wave? Well, how do we calculate the wavelength? The wavelength is the length of one wave. If I start counting here, how many waves do I actually have? So I'm going to count, so that's 1, 2, 3, 4. So there are actually 4 waves there. And so to get the wavelength, I'm going to take the distance divided by the number of waves. So I have 40 meters divided by 4 waves, and I end up with 10 meters as the wavelength. So if you just count, this is like 10, 20, 30, 40. So each wave is 10 meters long. Counting, you saw 10 waves pass the dot in 16 seconds. What are the period and the frequency? Ooh, another great question. So if we think about the period and frequency, the period is the time divided by the number of events. This time it's waves. And so it's 16 seconds divided by 10 waves passing. So we have 1.6 waves. Oh, just kidding. So it's 1.6 seconds for every one wave. To get the frequency, we're going to take the number of waves that pass and we're going to divide by the time it takes. So this time we have 10 waves pass by in 16 seconds. That's 0.625 waves per second. That's a period in the frequency. And these are obviously reciprocals. What's the speed of the wave? Great question. Well, let's use our wave equation that we developed in the lab, where the speed of the wave is equal to the frequency times the wavelength. Well, I have both of these over here, so I can just plug and chug directly. The frequency, 0.625, the wavelength, 10 meters, so the waves must be traveling at 6.25 meters per second. So if you were to watch a wave travel this direction, it could go 6.25 meters every second. You could watch it go. That's the actual speed of the wave, which is cool. All right, a couple more. Let's get rid of these. It says, electromagnetic waves travel through the vastness of space. The frequency of yellow light is about 5 times 10 to the 14 hertz, and the wavelength is about 6 times 10 to the negative 7 meters. Oh Lord. So let's break this thing down. Let's break this thing down. First of all, a lot of times you'll see frequencies measured in something called hertz. So for example, the frequency of this one is 5 times 10 to the 14. That's hertz. Now hertz just means waves per second. Now the problem is that this is 10 to the 14. This is 5 followed by 14 zeros. That means the frequency is so big, it's hard for us to comprehend. This is a crazy, crazy, crazy large frequency. Interestingly enough, though, it tells us that the wavelength is also a weird number. It's 6 times 10 to the negative 7 meters. Now, 6 times 10 to the negative 7 meters, 6 times 10 to the negative 2 meters would be 6 centimeters. 6 times 10 to the negative 3 would be 6 millimeters. This is 10,000 times smaller than that. This is much smaller than even the width of a human hair. So these are giant frequencies in tiny little wavelengths.
Hi, why do this?
I'm making a video for my friends.
Hi.
That's what I'm doing.
Now you need a pedal.
My computer's over here. Is that okay?
Why?
So what we're going to do is we're going to use our speed equation. So speed is equal to the frequency times the wavelength. We can just plug and chug because we have both of these. So this is 5 times 10 to the 14 times 6 times 10 to the negative 7. And this is equal to 3 times 10 to the 8 meters per second. And this is cool because this is the speed of light. It's the speed of any light, not only yellow light, but yellow, red, and all electromagnetic waves. So radio waves, infrared, gamma rays, X-ray, ultraviolet, microwaves even, they all travel at the speed of light, and it's 3 times 10 to the 8 meters per second. The next part says, how long does it take for yellow light to reach the Earth? So we're going to go with speed is equal to the distance divided by the time on this one. So the time would be equal to the distance divided by the speed. So the distance, it says, is 1495980. Oh Lord, I can't do that. Meters. And the speed is 3 times 10 to the 8 meters per second. And so when I go to calculate the time, I put this in my handy dandy calculator. I got 500 seconds. It says convert that to minutes, which is 8 minutes and 20 seconds. And what this means is that the light from the sun takes 8 minutes and 20 seconds to get to us. That has some weird ramifications, like if the sun were to blink out. If the sun were to blink out, we wouldn't know it for a full 8 minutes. That seems really weird. It also means that when we look at the sun, we're not seeing it like it is right now. We're seeing it like it looked 8 minutes and 20 seconds ago, which is really weird. And then, so this was 16, 17, and 18. It says which travels faster, yellow light or red light? And the answer is same speed. All electromagnetic waves travel at the speed of light, so no matter what color light you are, you travel the same speed. One may have a larger frequency, one may have a larger wavelength, but they travel at the same speed. And last one says, compare and contrast transverse and longitudinal, which are also called compressional waves. So we got to think about it this way. Let's say you took a slinky, and here's what your slinky looks like. And what I'm going to do is I'm going to take the end of this slinky, and I'm going to wiggle it up and then down, up and down, up and down, up and down. And when I do that, a weird thing happens, where you can send wave pulses that are moving this direction. The wave is actually moving this way, even though you're moving it up and down, and these are called transverse. That's the kind of waves you created with the waves on a string lab. However, if you took this same slinky and you started pushing it forward and back, so what you're doing is you're pushing it forward and then pulling it back, you can actually create a really weird thing where you have bunched up sections in between spread out sections, and bunched up sections, spread out sections, and bunched up sections. And what's happening is this wave These bunch subsections are actually moving through here because you're wiggling back and forth. And because the wave travels in the same direction that you're vibrating it, we call these longitudinal. But because they make these little compressions in here, they're called compressional. So transverse waves travel perpendicular to the direction of vibration, and longitudinal waves travel parallel to the direction of vibration. That's it. Hope you enjoyed the waves homework.